A couple lessons ago, we said that pretty much all types of energy can be sorted into two categories, kinetic energy and potential energy. Last lesson, we talked a bit more in detail about potential energy, specifically gravitational potential energy. And you'll recall that potential energy comes from an object's location. How much potential energy something has is dependent on where it is. Kinetic energy, you can recall back a bit further, comes from an object's motion. More specifically, you might ask, well, what aspect of the motion gives the object kinetic energy? And so more specifically, it is the object's speed that gives it kinetic energy. If you give an object a bit more speed, it has a bit more kinetic energy. If you reduce an object's speed, it'll have a little bit less kinetic energy. So we'll often simplify this if we're talking about kinetic energy and gravitational potential energy. We'll say gravitational potential energy comes from height and kinetic energy comes from speed. Now, with potential energy, or with gravitational potential energy in our previous lesson, I tried to draw this close parallel between energy and work. And we learned at the end of that lesson that gravitational potential energy is the amount of work that gravity has the potential to do. We can kind of make a similar comparison between work and kinetic energy. So kinetic energy is the amount of work that needs to be done on an object to get it from rest to its current speed. So imagine you see a car driving down the road, it goes past you, and you might be wondering, what's the kinetic energy of that car at its current speed? Well, that's the same as asking, if that car had been at rest and it had to speed up to get to the speed it's at now when it's going past me, how much work would we have to do on that car to achieve that? So how much work has been done on the car to get it to its current speed? That's the same as asking how much kinetic energy it has. So knowing this, we're going to figure out for ourselves a useful formula for calculating kinetic energy. So if kinetic energy is the work done to bring something up to speed, let's start with our work formula. We're going to calculate the work that needs to be done to bring some object up to its current speed. So work is force times distance. They need to be parallel. One thing I'll remind you about this equation is there are no vector hats. Energy and work are not vectors, they're scalars. Force is a vector, but we don't include the vector hat here because in this equation, we're just using the magnitude of the force. We're not using the full vector. And you'll find that going through this whole example here, I actually neglect all of the vector hats in all of the equations because what we're ultimately after is work. And that is not a vector. It doesn't have direction. And all of the equations that I'm going to put further down here on the page, I omit all the vector hats because I'm really just interested in the magnitudes. So what we're going to do with this equation to come up with our formula for kinetic energy is we're going to sub a bunch of stuff in. And I'm going to start with this force. I'm going to write that in a different way. And you might recall that force can be written as mass times acceleration. That's from Newton's second law, F equals ma. Then, now that I've rewritten force as mass times acceleration, I'm going to rewrite this acceleration as something different. And to help me with that, I'm going to use this kinematics equation. This is sort of our first of the big three equations. And if I rearrange this for A, I get Vf minus Vi divided by T equals A. So let's put that in over here for A. Instead of A, I'm going to have Vf minus Vi divided by T. And then my m is still here, as usual. Now, remember, we said kinetic energy was the work needed to get an object from rest to its current speed. So if we're starting from rest, that means Vi is 0. So I'm left with, over here, my force in this situation can be rewritten as the mass times the final speed, the speed that car is going at as it goes past you, divided by the time it took to get that car up to that speed. So that's the sort of the left side of this equation. Now we're going to take a similar approach over here to the distance. We're going to take that distance, we're going to substitute some stuff into it, and we're going to write it in a different way. For starters, I'm going to pull out one of my big three kinematic equations again. And I'm just going to say, I'm going to rewrite that distance as VIT plus 1/2 AT squared. That might sound a bit familiar. That's sort of our second equation from the big three, D equals VIT plus 1/2 AT squared. Then what I'm going to do is, just like I did over here, where I replace this A with VF minus VI divided by T, I'm going to do the same over here with this A. So this A became, after all was said and done, VF divided by T. This A also becomes VF divided by T. And the rest of the equation is the same. You'll also recall that over here, I said, wait, if we're talking about from rest, VI is 0. That'll apply over here as well. Then we're looking at this, we're saying, okay, this is a bit ugly. I got a couple of fractions. I got something squared. Can I simplify this a bit? And you might notice that, yes, you can. I have one t down here in the denominator. And I have a t squared, or a t times t, up here in the numerator. So one of these t's on the top can cancel with that t on the bottom, leaving me just a single t up on top. So what I've done here is I've said, OK, I can rewrite force as mass times speed over time. And I can rewrite distance as 1/2 times speed times time. So now we're going to take these two parts and we're going to recombine them again. Mass times speed over time, mass times speed over time. 1/2 speed times time, 1/2 speed times time. So I've just basically gone back to the form of my original equation. Work is force times distance. There's my work. Here's an expression for force, and here's an expression for distance. Then we go a bit further. And we say, well, hey, there's a t up here and a t down here. T in the numerator, t in the denominator. Those are going to cancel each other out. And then I have a VF here and another VF here. They're getting multiplied by each other. So that can just be a VF squared. So when I get rid of that t and I turn that to a VF squared, shuffle things around a bit, I get the work that is done to get a car from rest up to that VF speed, that speed when it's going past you. That work can be expressed as 1/2 times the car's mass times the speed it's going past you at squared. And that is another way of saying the kinetic energy, the work that's done to get it from rest up to that current speed. So when we call it kinetic energy, though, we're really just talking about the energy it has at that moment as it goes past me. We don't really care about what happened before that. So rather than thinking about VF and VI, we just call this V. This is the speed the car has right now as it's going past me. And if I use that, that gives me the car's kinetic energy. So the reason I wanted to show you this, rather than just giving you this equation on your formula sheet and letting you run with it, is I want you to realize that a lot of these equations aren't just coming out of nowhere. They're not mystery equations. They come from simple principles that you guys already know. So this equation for kinetic energy just comes from using the equation for work, using Newton's second law, and using a little bit of kinematics. OK, so kinetic energy equals 1/2 times mass times speed squared. We always want to talk about units whenever we come with a new equation. No big surprises here. Mass is in kilograms, speed is in meters per second, and kinetic energy, just like all types of energy, is going to be in joules. Again, a reminder about vectors here. Because we were starting with an equation that didn't have any vector hats in it, we knew that direction wasn't going to be important. So we ignored all the vector hats in our kinematics equations and in Newton's second law along the way. So what we end up with here is an equation with no vector hats. There's no information about direction in here because we threw all that out when we did this. So this v, although you might be tempted to call it velocity, this is speed. There's no vector hat on top of this v. This is speed, not velocity. So whether an object's going left or right or up or down makes no difference here. You would never put in a negative number for this. This is just the magnitude of the object's speed. In a previous lesson, I said that sometimes it's useful to think about energy as the amount of damage something can do. And we said, the higher you lift a rock up, the more gravitational potential energy it has, and the more damage it can do. You'd probably be a little more scared of that rock falling down on you if it was higher up. Same idea works for kinetic energy. If an object's coming at you with some speed, how scared you are of it, how much damage it could do to you, is going to depend on how much mass it has and how much speed it has. Is it a bumblebee going 1 meter per second, in which case you're maybe not that scared? Or is it a train going 30 kilometers an hour, in which case maybe you are a little bit more scared? So energy can often be interpreted as ability to do damage. So let's take this equation we have and try and solve a problem with it. The kinetic energy of a 2.1 kilogram rotten tomato is 1,000 joules. What is its speed? So this is really just an exercise in algebra. We have this equation for kinetic energy. We're given the kinetic energy, 1,000 joules. We're given the mass, 2.1 kilograms. Everything's in metric base units, so that's great. All we have to do is rearrange and solve for v. We have to isolate v. A little bit awkward because we got a fraction here and we got a squared there. So let's go through it step by step. First thing I would do is I would say, OK, this 1/2 and this m need to go to the other side. To undo multiplication by 1/2, I can multiply by 2. So that's where this multiplication by 2 comes from over here. And to undo multiplication by m, I can divide by m. That's where my divided by m comes from there. And I'm left with just my v squared on this side that I had to begin with. Next thing I'm going to do is I'm going to say, OK, to get that v by itself, I need to get rid of that squared. How do I do that? By taking the square root of both sides. But remember, whenever we take a square root to get rid of a square, the answer can be positive or negative, plus or minus. So I've taken my square root to get rid of my square, but my answer, I have to remember, it can be plus or minus. Now I think we're at a point where we can just plug some numbers in. So the kinetic energy is 1,000, the mass is 2.1, and I'll move over here so I have some more space. Here's my numbers plugged in. And we throw that onto a calculator. We're going to get plus or minus 30.9 is the speed. And we have to pick. We want the positive one or the negative one. Well, remember, speeds can't be negative. A velocity could be negative if something was going left or down or backwards. But a speed cannot be negative. So in this case, because we're looking for speed, we're just going to pick the positive number here. We're going to go with the positive one. So the speed of this tomato is 30.9 meters per second. The next part here asks, how much work has to be done on it to bring it up to this speed? So I got this rotten tomato. It's flying by me. It's got 1,000 joules of energy. It's going 30.9 meters per second. I might say, hey, how much work must have been done by whoever threw this tomato to get it going this fast? And often with a question like this, students kind of dive in and they go straight to the equations and they try and pull numbers from here and there. And They might complain and say, oh, there's not enough information in the question. But if you sit back and you just think a bit, the work done to bring something up to speed, that's exactly what kinetic energy is. Kinetic energy is the amount of work that needs to be done to get an object from rest to its current speed. So part B here is really just another way of asking for the kinetic energy. And that was given to us right in the problem to start with. So we just put it right down there. No equations, no algebra, no math, just recognizing that there's this link between work and energy. The amount of work that needs to be done to get something up to speed is the kinetic energy it has when it's moving that speed.